All right, this is the toughest question on the paper, and just bear with me because it's quite challenging to explain. Okay, here goes. I'm just going to set the scene to start with. Actually, I will include part A. I'm just going to move it down a little bit to the bottom. Okay, we've got an underground tunnel, first of all, and it's got some points on it. So let me draw the tunnel here. P and Q. They're on the ceiling of this tunnel. We're then told that a ventilation shaft must be dug from the point M, which is the midway between P and Q. Now immediately I could find out what M is, and it's worth doing this sort of thing, you know, just it's probably going to come in at some point, but let's just find out information that we can. So you can either look at the number halfway between 3 and -1, which is 1, or you can add them together and then divide by 2. I'm not going to spend a long time on this, so it's going to be 4, and then this one's -18.5. We're told that a ventilation shaft must be dug from the point M on the ceiling between P and Q. Sorry, M on the ceiling of the tunnel midway between P and Q to horizontal ground level. So I'm going to put a horizontal ground level here. And then here's my ventilation shaft. It says it must be perpendicular to the tunnel, so this is a right angle. I might label this as G for ground. The path of the ventilation shaft is modelled by the vector equation R equals A plus lambda B, where A is the position vector of M. So remember, when you write these equations down in vector form, you start at the origin, you get onto the line, we're getting onto it at M. So we can write down for the ventilation shaft that R is going to be 1, 4, minus 18.5. Again, I'm just writing things down that I know, plus lambda, and we're actually also told what B is, 1 ST. Okay, we've got that information so far. Now we need to show that S is equal to 2.5 T minus 2. How can we do that? Well, one thing we've not yet done is write down the equation for the tunnel. So let's have a go at that. So for the tunnel, we could get onto the line at P, for example, or we could get on at Q. And then we're going to go along some distance either this way or the other way. And essentially you can just subtract them to get the direction vector. So I'm going to do P minus Q. And actually I think that would be Q to P, but that's fine. So it's going to be 3 minus minus 1, 5 minus 3, and minus 21 minus minus 16, which is minus 5. And that is so that we get onto the line at P this time. We go along some amount of this 4, 2, minus 5, which means we need another parameter there. We've got two equations. We've got our equation of our ventilation shaft in the red, and I probably should have made it red to be fair. And then we've got the equation of our tunnel in blue. Now here's the thing we've not used yet. So we've got to kind of find any piece of information that is useful, and it's the fact that they're perpendicular. So two vectors that are perpendicular have a special property, and that is that the dot product is going to be 0, because the A dotted with B is equal to the magnitude of A times the magnitude of B times cos theta, the angle in between them, equals 0 when theta equals 90. Now it's going to be the two direction vectors that are perpendicular. As I was saying, the direction vector takes us from M towards G. Okay, some amount, and the direction vector of the tunnel takes us from either P to Q, towards P to Q or Q to P, some amount. So it must be that 1st dotted with 4, 2, minus 5 is equal to 0. Now I can use the alternative version of the dot product, and that is to actually just multiply these values. I'm not going to prove this, but you can basically multiply the x ones together, then add the y's, and then the z's. So that means that 2s is equal to 5t minus 4, and s is equal to 2.5t minus 2 as required. Okay, brilliant. Got part A sorted. That was quite a lot to do just for that starting part. Okay, show that at the point where the ventilation shaft reaches the ground, lambda is equal to c divided by t, where c is a constant to be determined. So remember, where it reaches the ground is where z is equal to 0. So what we can do is we can take this equation for the ventilation shaft, and we can actually just look at the z component and set it equal to 0. So when z is equal to 0, 0 is going to equal minus 18.5 plus lambda t. And that means that lambda t is equal to 18.5, which means lambda is equal to 18.5 divided by t. C is equal to 18.5. Taking good strides forward in this question. So C, using the results, it's going to be the hardest one. Using the results from parts A and B, determine the shortest possible length of the ventilation shaft. Okay, let's think about this. So the ventilation shaft is from M to G. And actually, we know what mg is. It's simply this lambda times the direction vector. And we want to find shortest possible This is how you write down the magnitude of a vector. Okay, how to do that? That seems quite challenging. We've got a s, we've got t, we've got lambda. But here's the thing, we know some relationships. We know that we always have s equal to 2.5 t minus 2. And we also know that when, at this point here, g, lambda is equal to this 18.5 divided by t. So we can substitute that in, and that will help us work out the length. So actually mg is going to equal 18.5 over t, then 1. Here we have 2.5 t minus 2, and here we have 2. Now I'm going to take this steady, and I'm actually going to multiply this inside. Okay, there are ways of doing this question where you don't, if you look at the mark scheme, you don't even multiply it inside, but I think it's clearer if you do, personally. So it's going to become 18.5 over t, and then 18.5 over t times 2.5t minus 2, and then just 18.5 here. Now, if I was to find the length of this, then what I would do is I would do this squared plus this squared plus this squared, all square rooted. And that's going to be all in terms of t. But we want to find the shortest possible mg. And actually, I'm going to throw it out there now. This is a calculus problem. Actually, it is possible to do this without calculus, but it's probably more complicated. Actually, if you look at the mark scheme, you can do it. But we're going to go with calculus. It's kind of always a good idea if you see things like minimizing. It's a good shout. But minimizing something that's square rooted doesn't look very nice. So actually, we're going to find the minimum, or investigate the minimum, not of mg here, but the length squared, because then I get rid of the square root. So mg squared is actually going to be 18.5 over t squared plus 18.5 over t 2.5 t minus 2. Both of them have got to be squared, plus 18.5 squared. And actually, we're going to work this out in terms of t. I'm just telling you where we're going with this. And then we're going to differentiate with respect to t and set it equal to 0. That will allow us to work out the value of t, which gives us the minimum value of the length squared. And the minimum value of the length squared, well, if that's the case, that value of t must also give us the minimum value of the length. To go together. So this is looking not particularly nice, but we can, we've got a calculator, let's figure it out. So 18.5 squared, I'm going to work in terms of decimals, 342.25. And it's going to become divided by t squared, which is t to the minus 2, plus 342.25 over t squared. Now I've got to expand this bracket. 2.5t times 2.5t is 6.25 t squared. I've just realized I've massively run out of room. And then I'm going to do 2.5t times minus 2, which is minus 5, and then do another one, so we'll get minus 10t plus 4. Then plus 342.25. Okay, now I can multiply this by 6.25. 2139 0.625. And these t squareds are going to cancel, so I'm just left with this constant. Then it's going to be minus 342.2.5 t to the minus 1, because I'm doing t divided by t squared, plus this thing times 4, and 369. Okay, so I'm actually now finding d by dt of mg squared. And this will equal, here I'll have to times through by minus 2. Minus 684.5. T to the minus 3. Actually, the constants that I spent ages calculating will just disappear. And for some reason, why did I not combine that? Okay, I should. Before I differentiated, should have combined the t to the minus 2s. I just didn't spot it. All right, it's fine. So minus 2,738. And then plus. So these are going to disappear, but when I bring the power down, it's going to become plus 3,422.5 t to the minus 2. Okay, let's just bring this together. So I've got that, and then I'm going to minus 684.5. Aha, this is brilliant, because actually I've got the same number. So it's going to be 3,422.5 over t squared minus 3,422.5 over t cubed equals 0 for minimum. What we can actually do is times through by t cubed. So 3,422.5 t minus 3,422.5 is equal to 0. And actually the answer is as simple as t equaling 1. Now we're not done actually, but that is going to be the value of t that gives us the minimum possible length squared, and hence the length. So now we just need to work it out, and it's probably best to return to here actually. Just going to write it down. So t gives minimum length. Now, technically, we've not proven that it's a minimum, but there is going to be no maximum. Like you can kind of see it from the questions, and it's absolutely fine. Let's just go with it. Okay. So it's going to be 18.5 times by 1, 0.5, and 1. So for min. Okay, and we can then just do 3D Pythagoras, square and add them. Actually, because there's 2 lots of them, I can just times it by 2. And we get 27.75. Have we even said what units we're working in here? not clear, so I'm just going to leave it like that. Just one thing to say, I could have actually done this. I mean, you can do this question quicker. I think it's harder to understand what's going on, but there's less decimals and everything. I'm going to talk about like one idea that you can use. So if I wanted to find the length of 18.5 times this vector, I could have actually done 1 squared plus 0.5 squared plus 1 squared square rooted, and then times that directly by 18.5, because it's like I'm finding the length of this vector, and then of course if I times that vector by 18.5, it makes it 18.5 times as long. So I didn't have to do what I did there. I just didn't want to go into that level of complexity at the time. And you can actually do it in the solution if you want to. Now, again, I decided not to, but I could have actually have, instead of timesing these, I could have done this squared plus this squared plus this squared, square rooted technically, and then times it by that. So if I wanted the length squared, it'd be this squared plus this squared plus this squared in a bracket times by this squared, and then you could you could potentially like simplify it and multiply it through, and it would come out slightly nicer than all the decimals I've got. I just thought I'm trying to make my explanation really clear here. That's the answer anyway. That is awkward, it's got to be said. We're not done. Last little part. Explain what the fact that the cross product between B and 0, 0, 1 not equaling the zero vector means about the direction of the ventilation shaft. Okay, well, let's just take a little look at this picture again. So, by the way, the main thing to remember is when you find the cross product, you find a vector which is perpendicular to both of the vectors in question. And so the fact that it's, well, basically, if it's equal to the zero vectors, they would both be parallel. And actually, I've kind of given you the answer there. This not equaling 0 means that B is not parallel to 0, 0, 1, i.e. the ventilation shaft is not vertically up. The 0, 0, 1 vector is the Z vector, and it talks about the fact that so Z is going to be this way. It says the Z coordinate is 0 at ground level. So basically, i.e. ventilation shaft is not vertical. This kind of comes from the fact that it talks about the Z coordinate being 0, so that's why this way is going to be the Z axis, whereas often obviously it's the Y axis. So something like this. I'm just going to actually quickly flick to the mark scheme. So it says here, so yeah, B is not parallel to the Z axis, so the ventilation shaft does not go straight down. I just want to show you actually the way they did it in the answers. So they said to minimize this thing here, and then they squared. They did Pythagoras on this part without square rooting, and just squared this 18.5 over t, left it as a fraction in fact. And it just actually turns out that, well, when you differentiate, you can actually carry it through as a constant. That's one reason this is good. And actually, you just get this really nice thing inside the brackets to get t equal to 1. So it is simpler than what I did, but it's a bit harder to understand. The second method is here. I'm not going to talk about that anymore, but that was another way of getting 27.75. Anyway, hope you're happy with that question. Bit of a tough one, but yeah, it's a good one. Thanks.